All right. So my name is Pranav Durai. I am a computer vision engineer at OpenCV, and I'm also a research fellow at Stanford University School of Medicine, Palo Alto. I'm also a member of the Computer Vision Foundation. So it's really my pleasure to be a part of today's session organized by NIT-K and NIT Karnataka IEEE student branch, right? So before we get into today's, keynote on a gentle introduction to computer vision using OpenCV, I'd like to give you a small intuition of computer vision with the kind of work that I do on a daily basis, right? So this will kind of set a bar to understand what is going on in the cutting edge research and development for computer vision. And then we'll try to understand what it is and how do we do it and so on and so forth. Does that sound interesting? So what am I working on right now? So at OpenCV, I'm actually developing advanced driver assistance systems, which is also ADAS, right? So you have seen autonomous self-driving cars which can navigate through the roads by themselves without, any human intervention, right? They can, drive on their own. But how do they do that, and what kind of systems are necessary to facilitate these vehicles to see and navigate by their own, right? So this is one project which I've worked on the left, which is real-time lane segmentation, right? So given an input video stream of a POV camera stream from a vehicle, the system should be able to identify and segment out the lanes effectively from the video stream, right? So it is important because you have to change lanes when you're traveling from point A to point B, right? So you have a vehicle in front of you and you have to brake, or you have to change lanes because this vehicle is too slow and you want to go fast. There are a lot of things, and lane segmentation is very important. And this is a system which I've built, which can not only segment lanes during the daylight, but it can also segment out lanes effectively during nighttime, right? So that was a pretty good project which I worked on. And let's have a look on the right. So we do know that as humans we have two eyes, and this is kind of a stereo vision that we have, which we use to perceive the real world in 3 dimensions, right? But cameras can't really do that, right? So they interpret the world in 2 dimensions. But then if you use those kind of cameras on vehicles which require high amount of safety, that's not really the right thing to do, right? So that's where LiDAR comes in, right? So you use a sensor such as LiDAR, which can project laser beams 360 degrees from where it's fit, right? And it can generate a 3D point cloud of what it's trying to see, right? So basically points, objects which are closer to it will be, the points will appear closer, and the objects which are far away from the sensor will appear far. The points will appear far. And that's how you generate a 3D cloud representation of that specific scene. And what I've done over here is that the input image is a 2D depth frame, right? So it's a 2D depth frame from the LiDAR sensor. And each of those values, you see a grayscale image over here, right? I'm sorry that it's pretty fast, but it is a moving image. It's a GIF, right? So it's pretty fast. So you see over here, yeah. So that is the 2-dimensional, depth map that the LiDAR system gives. And you use that to, kind of generate this 3D LiDAR visualization, right? And this will be used to perceive the real world in 3 dimensions so that the car or the vehicle can move and navigate through obstacles that it sees in real time. So this is actually the POV view, this is the side view, and this is actually the top view of a street in which this car is moving in, right? So this is going to help very much for full self-driving autonomy for cars that are driverless, right? So this is what I'm working on at OpenCV. At Stanford University School of Medicine, I'm serving as a research fellow, where we are actually developing a system that can assist with the early detection of cancer cells in human beings using PET-CT imaging, right? So PET-CT is used to visualize the internal organs and structures of a living body, right? But the thing is, if you're trying to experiment on living beings, you need to have medical clearance to do that. But since this is a lab trial, so all of these experiments were done on mice, right? So you can see that there are it's a four bed PET-CT imaging output that you see over here, which I am highlighting right now with my cursor, and which means there are 4 mice over here, right? And you use this image to segment out organs and cancer cells from this internal structure, right? So basically, they identify mice which have cancer cells within them for a region of interest organ, and then researchers are developing antibodies to kill cancer cells within living beings, right? So they inject that into the mice, and they try to see if the cancer cell dies or not, right? So that is basically the main motto of this specific project. You're trying to segment out organs from the animal, plus you're trying to segment out cancer cells within that organ. And during a period of time, you're able to visualize and try to understand if the cancer cell becomes smaller or it dies or it still exists. And that's when you realize that, hey, I want to change this medicine into something else with a different formula and try to experiment with that. All right, so this is what I've been working on in terms of computer vision. So is this something that interests you? Are these interesting applications? So let's dive deep and let's have a one-on-one introduction to what is computer vision, right? So there are a lot of folks over here. Anyone who wants to define what is computer vision, you can use the chat box to do so. So how would you define computer vision? Looking at the examples that I've just showed you. All right, let's check the chat box. In simple terms, it allows a computer to see and process images similar to how a human brain does, right? Yeah, it's very similar. Thanks for the answers. So this is how I would, define computer vision, right? So it is the technology that enables computer systems to see and perceive the real world like how we humans do, right? It's very similar to the comment on the chat box. So basically, it enables computers to see and perceive the real world just like how we humans do, right? But how are these systems able to do that, right? How are these complex systems able to do it and be able to see and perceive, right? But for that, let's understand the fundamental aspects of images. And images are very important for computer vision, right? Anything that happens in computer vision happens on an image. So let's have a look at images. So how is an image represented, right? So you can see that you have a very bad image over here. It's a face of a person, right? And you also have values for each of these building blocks over here, right? So you can see numbers within each of these building blocks, right? So these are black building blocks, right? Black building blocks. You have gray, you have white, you have a little more lighter version of gray over here. You have pure white and just pure black, right? So all of these building blocks are, represented using some kind of value, right? And you can see that it ranges from 0 to 255. So for example, this complete black building block over here is represented by 0, which means it's completely dark. And on the other hand, if you see some pixel over here, So this is 251, but there is another pixel which is 255. Oh yeah, there is 255. So that is complete white. So this is how images are represented digitally. So basically, images are digitally represented as two-dimensional matrices, right? So you have a matrix representation of a digital image over here. So that is how images are represented, all right? Okay. So I kept mentioning the term building blocks, right? So building blocks are nothing but pixels, right? So each image is constructed using pixels, right? So if you can see over here, there is a representation of how a pixelated image can be, the density of the pixels can be increased to increase the clarity of that specific image, right? So you can see over here. You have larger pixels in the beginning, and as and when the pixels are becoming smaller and more in number, we can see that the image is more clear, right? So the same thing is happening with this 8-bit character as well. So images are constructed using pixels, all right? Now, if you remember those old television sets that you had back at home as a kid, those CRT big boy televisions, right? So I'm pretty sure that everyone has gone really close up to the screen and you've seen these colors popping out. So these are nothing but the pixels themselves, right? So back in the day, the pixel density of those CRT screens or CRT televisions was very low, which means the number of pixels per square inch of that screen was very less, right? So you were able to actually see those pixels with your naked eye, right? So this is that over here. And you can also observe that these pixels are made using three main components, right? So that is red, green, and blue, right? So RGB, right? So then that is how these pixels are represented. But now, in the current generation, you do have LED and LCD displays, and the number of pixels, which means the total density of pixels per square inch of that screen is very high. So which means even if you go closer, you won't be able to actually see these pixels with your naked eye. You would require a magnification lens or something of that sort to actually have a look at them. And that is also why it's able to display content in full HD, 2K, or 4K resolutions. Right? So the more number of pixels, the resolution increases, and you get a high resolution image with breathtaking clarity and colors. Right? So all of these pixels, right, they form together as channels. Right? So images are made up of channels. And each image over here, so we have a picture of an apple over here, and this is made using red, green, and blue channels, right? And you can see that each of those channels have their own values over here, right? So these are three different two-dimensional matrices, right? So when you merge them, you get the entire RGB image. So you can see that this top left corner of the red channel shows 253, and the same pixel corresponding to that in the green channel shows 23, and the same pixel corresponding to that in the blue channel shows 60. And when you merge these matrices together, you get this pixel over here, right? So this is what it's trying to represent using multiple channels, right? So just using three channels, you're able to, manipulate and try to create new colors and try to visualize the image as it's meant to be. All right. So images are made up of channels, and these channels can contribute to multiple spaces, and that's what we call as color spaces in computer vision. Right. So which means images can be visualized in different color spaces. So in the current generation, we have close to 4 to 5 different color spaces. But in this specific presentation, I'll be showing you 4 color spaces, right? So you have RGB, which I showed you previously in the previous slide, and you have CMYK, which stands for cyan, magenta, and yellow, right? It's a different component of colors, composition of colors, right? You have HSV, which stands for hue, saturation, and value, and you also have YCRCV, color space, all right? So each of these color spaces, they are meant for different use cases, right? So it's not that one color space works for everything, right? That's not possible. So RGB and CMYK are used mainly for consumer applications. Right? So the monitor that you're using right now to view this presentation uses sRGB. Right? So that is a standard which all of the consumer displays should have. Right? CMYK is very famous for printing applications. Right? You're trying to print a poster, you're trying to print visiting cards and stuff like that. All of those professional industry grade printers, they use CMYK so that the colors are pretty appealing when it comes out of the printer. Right? Now HSV is actually used for image segmentation, right? And I'll talk more about image segmentation in the upcoming slides, but basically it helps you to segment out different parts or different regions of pixels from an input image, right? And YCRCB color space is actually used for face recognition. So it turns out that people from all over the world, right, they have different skin tones, right? And if you're trying to build a face recognition system, then it should not have any racial bias, right? So it should be able to, completely, recognize the face as it's meant to be. And it turns out that YCRCB has the ability to show skin tones from an input face image. And that's why it's more, capable of better face recognition performance than the other color spaces, right? So these are color spaces in images, right? So now we did understand how an image is made of, what a pixel is, and what each of those channels are, and what the color spaces is, right? But a very important question arises is that what are the applications of computer vision, right? I'm pretty sure that most of you are new to computer vision, right? It is an upcoming technology which has great amounts of potential. And what are the applications of computer vision in the real world? So let's have a look at those as well, right? So the first one is object detection, right? So let's say that I want to detect few objects of interest from an input video stream. I can do that, right? And each object will be treated as a class. So let's say that I want to detect 3 classes or 3 objects. So a car, a pedestrian, and probably, let's say a truck, all right? So 3 objects. So this is actually a 3-class image object detection problem. Right? So you're trying to detect objects from a specific video stream. Right? So that is the exact thing that is shown on this example image over here, example illustration over here as well. So you can see that in real time, the object detection model is able to detect objects of interest from that specific video stream. Right? So it draws bounding boxes around the objects that it thinks as a car, a pedestrian, and a truck, right? So that is what is shown over here as well. And on the right, it's the complete opposite, right? You're not trying to detect these objects, but you're trying to segment out these objects from the input video stream, right? So basically, you can see that you have an input stream of video over here on the top, right? And you have color matching codes for each of these segments on the right. So let's have a look at it here. And then you pass this top input stream into a segmentation model, and it's magically able to segment out the pixels which belongs to that specific class. Right? It's not just detecting the object, but it's doing pixel-wise analysis, pixel-wise detection of objects in real time. And that is called segmentation, right? And it's also showing the same values of colors that it has to match, right? So this is a person, you can see that it's in red over here. And you can also see vegetation. So you have trees in the input stream, and that has been visualized with masks with green color. And there are few cars over here. And what is a car? That's blue, right? So that has been masked with blue color over here, right? So this is object detection and segmentation, right? So most of you, go to the gym and try to keep yourselves healthy, right? But it turns out that posture is very important. So when you're trying to lift, heavy lifts, right? It's very important that you do it in the right way so that you don't get muscle cramps, right? And for that, you do have a trainer, right? You pay extra and you get a trainer, and that guy assists you with the right posture, which you need to use to do your exercises. But that always isn't the case, right? What if the gym is empty and you're the only one there, and you want accurate representation? Now, this is one example of one such example of key point estimation, right? So basically, what happens is in a key point estimation model, let's say for human beings, it maps key points in specific regions of the human body, right? So you can see one over here in the joint, right? And the other in the joint over here, and 3 points over here for his feet, right? And this is for his hip, right? This is for his upper body region. You have few points, and you have few joints over here as well in the arm region, right? And few points in the facial region as well. And in real time, it's able to track and estimate these points in 3-dimensional space, right? So this is 3-dimensional tracking of key points in a specific input stream of video, right? And a little bit about image processing, right? So we do know that you can use tools like Photoshop to enhance images, right? So it has multiple features for blemish removal and image restoration, basically trying to make your image way better, right? And that is another application of computer vision. Face recognition, and this is pretty famous as well. And I'm sure that most of your smartphones these days have some sort of face recognition system, right? Apart from the traditional PIN code authentication, right? So basically, it uses a very similar system to what I showed you in key points, where points are mapped on your face, right? On the front side of your face. So which means eyebrows, this region has a specific, some specific points, right? The eye region has specific points, nose, mouth, and this shape, right? So the shape face is different for each individual. So that again is mapped using points, and a face recognition model is able to, understand the points and the position, and will try to correlate it with the RGB image and try to get an understanding of, hey, this is how Pranav looks like. This is how this person looks like. This is how that person looks like, right? And it's been trained on thousands of images of your face, and it's very accurate in detecting and recognizing faces, right? So that is face recognition. And if you've used tools like Cam Scanner, you do know that it's able to scan. It's able to scan a document and convert that into a digital representation, after which you can edit it, right? So that is possible through OCR, or optical character recognition, right? So this is a very famous technology, and it turns out that close to 40 to 50% of the industries right now use computer vision only for optical character recognition, and that is mostly because most of these documents were in physical format, right? So especially in banking sectors where they try to do KYC for opening a new document, right? So probably 5 or 10 years ago, all of these documents were physically, managed. But then now people are, realizing the potential of the digital era, and they're converting all of these physical documents into digital footprints. And now, how would you do that? Because you have millions of documents, millions of physical documents, and most of them are really old as well, which means they have a lot of wear and tear. It's not in its proper condition. And how do you effectively extract out 100% data from those bad documents and have a digital footprint of it, right? So that is an open research problem. I mean, there are multiple OCR models which can do that, but you require a lot of pre-processing and fine-tuning to get the best result possible. All right. So that is OCR. All right. So let's talk about OpenCV. How many of you have used OpenCV before? Okay. I guess 10 of you. 10 of you out of 100 folks. That's great. So let me talk to you a little bit about the history of OpenCV, and then I'll start to talk about a few features that OpenCV has. Right? So OpenCV was actually launched in 1999 or 1998, right? It was actually a project by Intel, so the famous semiconductor manufacturer, right? Intel. So it was actually an internal project developed by Intel for computer vision. And after 2005 and 2006, it became an open source project, which means people from all over the world can contribute towards the project and get better versions of it. Until now, it's remained as an open source library. Right? Millions of people use it on a monthly basis, which means we get close to 2 million downloads per month for OpenCV itself, right? And the first autonomous car, which won the Dakar rally, used OpenCV to perceive the real world and navigate through very harsh terrain conditions. The first autonomous car was actually built using the ADAS system was actually built using OpenCV. So that is a small introduction about OpenCV, and let's have a look at the features. Right? So what are the core functionalities of OpenCV? Right? So it gives you a platform to perform image processing. Right? So the basic stuff, cropping, reading an image, displaying an image, and all of this applies for videos as well. Right? So videos are basically a sequential representation of images, right? Played in a specific time frame or time period, right? So that is called FPS. But not just that, but OpenCV can also do resizing of images, rotation, cropping. And you also saw that we could visualize images in different color spaces, right? Not just that, but you can also do thresholding. And if these terms are pretty new to you, don't worry. I will talk more about this in the hands-on session, right? So you can also do image filtering, try to apply different filters on images and try to get details out of an input image. You can perform multiple types of transformations. There's also a feature called contours, where you can detect contours in a specific image, right? Which is actually used for object detection, right? So these are classical computer vision techniques, right? So there's no use of AI within this framework, right? So you're basically trying to do manipulation and trying to get, data out of images, right? Which you've never seen before. And so those are few image processing stuff that you can do with OpenCV. Right? We also talked about video analysis, which means all of these things that is possible for images can also be done on video, right? You can also perform camera calibration, right? So the thing is, if I'm sitting inside a car, I'm behind the windshield, right? So what if I have a camera in the hood of the car, right? The hood on top of the hood on the car. The distance between me and the camera is different, right? And what if I want to make that camera look at the same POV in which I'm perceiving the real world, right? So you can do that using OpenCV as well. So camera calibration is possible. And high-level GUI, right? So basically, when you're trying to build computer vision applications, there are wrapper functions within OpenCV which allows you to build GUI, small GUI applications as well, right? So it's not just that you're dealing with these applications through command line interface, but it also allows you to bring in sliders, buttons, and interactive components to help you interact with your computer vision application, right? It's not just that, but it's cross-platform compatible, which means it runs natively on Windows, Linux, Mac, and Apple Silicon, right? So if you have an older Mac that runs on Intel, and newer Macs these days run on Apple Silicon, right? Yeah, and the last thing is 3D reconstruction, right? So in one of my previous slides, I showed you how we could use two-dimensional depth maps of a LiDAR sensor and then turn it into a 3D reconstructed scene, right? So that is also possible using OpenCV. Okay, so these are few core features and functionalities of OpenCV. So if you want to connect with me because you like the work that I do, or that's something that interests you, or if that is your own domain, right? If computer vision is your domain, you can connect with me. You can follow my work. You can just Google my name, Pranav Durai, and you'll have links to my LinkedIn, GitHub, and Google Scholar, right? So that's it. Thank you very much. Thank you very much for having me, and I hope you had a great weekend. Yeah, thank you.